The purpose of our experiment is to demonstrate the effect that temperature has on mass transfer, and we do this by dropping food coloring into plates of water at different temperatures ranging from ice cold to nearly boiling, and then measuring the rate of diffusion as the food coloring spreads out on the plate in terms of area per second. And the relationship that we're looking at here between temperature and mass transfer can actually be observed in many everyday processes. For example, marshmallows dissolving in hot chocolate or tea bags diffusing into hot water. In both of these processes, temperature has an important role in the mass transfer that's occurring. The use of hot liquids as opposed to cold liquids means an increased rate of diffusion, meaning either a softer marshmallow for your hot chocolate or a more flavorful tea. So what is mass transfer? We can define it as the movement of a chemical species from an area of higher concentration to an area of lower concentration in order to reach equilibrium. And it can occur in two different forms: diffusive mass transfer or convective mass transfer. And diffusive mass transfer is the movement of a species due to random molecular motion, otherwise known as Brownian motion. And convective mass transfer is the movement of a species due to the bulk flow of a fluid. And in this experiment specifically, we're mainly looking at diffusive mass transfer.
All right, so there are a couple of different equations that we can use to calculate the diffusivity of liquid solutes in liquid solvents, the first of which being the Stokes-Einstein equation. So this is a pretty simple equation, and all we really need here from the solute is the particle radius. Now, the other parameters are also simple to obtain, but the kicker here is that we have to make a couple of assumptions about the system that doesn't truly depict what's going on, including the radius of the solutes. Now, there's also the Wilk-Chain correlation, which also models liquid solutes in liquid solvents. But the kicker here is that we need the molar volume here of the solute. Now, while the Stokes-Einstein equation does a really good job of modeling what's going on, the Wilk-Chain correlation does an even better one. The only thing here is that the molar volume is often difficult to estimate for the solute when there are multiple compounds. But let's shift our attention to the Stokes-Einstein equation again. Now, the first thing you'll notice is that there are a couple of constants that we can take out of the system and lump into the generic constant C. So now that we're left with temperature and the viscosity of the solvent, which for our experiment here will be water, we can take a look at some experimental data for viscosity with increased temperature. And we can see that it decreases relatively linearly with temperature. And when we make this assumption, we can say that the diffusivity is directly proportional to the temperature. And this will be our main focal point of our experiment today.
Our experiment had a simple and effective way of physically showcasing how mass transfer and temperatures are related. We started with a plate that had a small amount of water on top, then added 1 drop of food coloring. After about 2 minutes, we then measured the amount of displacement that occurred on the food coloring. This was obtained with playback footage while using the plate size as a reference. From that, getting the diameter of the food coloring and knowing that the time it took, we were then able to calculate the rate of diffusion. We then repeated this test multiple times at temperatures ranging from about 5 Celsius to about 80 degrees Celsius. Then created a correlating graph comparing the measured rate of diffusion to its temperature.
Here we can see a demonstration of the difference in total area of diffusion. On the left is water at 5 degrees Celsius and on the right at 73. And as you can see, the hotter water presents a much larger area of diffusion.
We were able to collect data for 34 temperature values. When plotting these points on a graph comparing them to rate of diffusion, the points make a linear correlation. Some observations that we can make from our data was that small bubble-like regions were found at higher temperatures, and this is possibly due to small amounts of boiling water. There was also an unclear boundary and uneven diffusion, probably due to higher molecular activity or bulk fluid flow. Some possible errors that we may have had was that the diffusion area was more difficult to estimate at higher temperatures. The size of the drops may vary, the height of the drops may vary, and also the position of the drop was not always perfectly centered. Using the same temperature values that we took our data points at, we were able to calculate diffusion coefficient using the Stokes-Einstein equation, and we compared this to our experimental values. The mean absolute error between these two values was about 1.52 times 10 to the negative 6 meters squared per second. The mean absolute percentage error was 8.95%, and 96% of the variation in experimental rate of diffusion was dependent on temperature.
Overall, we had a very successful experiment since we saw an observable and measurable difference in the area of diffusion and the temperature of the water. Our R-squared value of 0.96 tells us that the y, in this case, our rate of diffusion, is very dependent on x, in this case, our temperature. And this is good, given that we observed a linear correlation. Future improvements we can make to the experiment is to standardize all the parameters of the drop, its volume, its height it's being dropped from, and the position on the plate in order to achieve more consistent results, to place distance markers on the plate to eliminate the need for further calculations after the video has been taken, and to provide constant temperature monitoring to observe how the temperature behaves and if this affects diffusion in any way. There are lots of chemical processes that rely on temperature-dependent mass transfer, such as separation processes, reactor design, and some materials in pharmaceutical manufacturing. This is why it is important to understand these concepts, because a lot of the things that we deal with in chemical engineering are based upon fundamental concepts like this. Thank you very much for your time, and we hope you enjoyed our video.